Okay, so just for, since I'm just starting the recording, we're looking at neutralization reactions. I was just saying that you should be able to solve these types of problems where you're just saying what is the pH of a solution of an acid or a base, where you just have one or the other present. In a neutralization reaction, essentially you're asking the question of what happens if I have both present? And in that case, you have to consider the actual neutralization reaction that takes place. So we're looking at this question here, which is what is the pH of a solution made from 0.1 moles of sodium hydroxide and 0.1 moles of HCl, and we're adding that to a liter of water. Okay, so you can imagine you have this flask of water, and I take 0.1 moles of sodium hydroxide that I've weighed out, and I dump it in. I take 0.1 moles of HCl, and I dump that in as well. And so this we just work out like we would work out any reaction. So you notice I'm putting this L after water. That's just to remind you that that is a liquid. So if we do end up using equilibrium constants, we don't have to worry about it. Here we don't have to worry about that at all. All right, so this is essentially like a normal limiting reagent problem that you would work. I start out with 0.1 moles of sodium hydroxide and 0.1 moles of HCl. How much of each of these do I have left over at the end is essentially, that's kind of the question that we're asking. So at the start, we have this, and then when the reaction is finished, how much do we have? Well, these react stoichiometrically, 1-to-1. So I have 0 of that and 0 of this, and then I would form 1 mole of water, which we're not super worried about, and then 1 mole of sodium chloride as well. So these are just reactions that go to completion, essentially. Oh, not 0.1. So this is the start. I have this much of each. I see how they react. They react 1-to-1. For every 1 mole of sodium hydroxide I have, it reacts with 1 mole of HCl to form 1 mole of water and 1 mole of sodium chloride. And so at the end of the reaction, I'm not surprised to see that I have 0.1 moles of water that have formed and 0.1 moles of sodium chloride. So what is our pH? So to figure out the pH, now we want to consider how much acid and base we have left over in solution. How much do we have? We have essentially none. How much base do I have? 0. How much acid do I have at the end of the reaction? 0. So this is essentially the same as asking what is the pH of a 0.1 molar solution of sodium chloride. So we're in 1 liter, so I'm just going to quickly convert that to molarity. Yeah, I'll put some problem solving videos on YouTube. I made some of those this morning. That's why I was a few minutes late to class. I was finishing up one. I'll upload those after class, and I'll upload this lecture. All right, so all that's in solution is 0.1 molar sodium chloride. So what's our pH going to be? It's another way of asking the question is like, what is the pH of a 0.1 molar solution of sodium chloride? Okay, so sodium chloride, is it acidic or basic? The answer is it's neither. Yeah, none. Thank you, Sahaj and Maria. Sodium chloride doesn't change the pH of anything because the sodium cation is the conjugate. You think of it as the conjugate of a strong base, and this is the conjugate of a strong acid, so they form just a neutral salt. And so what is our pH for the solution? It's just going to be equal to 7. So it's another way of asking just what's the pH of pure water. You know that sodium chloride is formed because it's sort of almost by definition for an acid-base reaction. So in an acid-base reaction, sorry, I should have done a better job of explaining that. In an acid-base reaction, and it changes a little bit because it's not always hydroxide and chloride. or it's not always hydroxide, I guess I should say, is the base. Mark the wrong thing. There we go. The proton from the acid and the hydroxide from the base come together to form water in this particular one. So the acid and base react essentially. And then the remaining species, the chloride and the sodium, just come together. To form a salt. Sodium chloride is neutral because Na is from a strong base and Cl is from a strong acid. That is correct. Yeah. So you can have acidic or basic salts, right? Like, I know this is confusing, but you can have acidic and basic salts. For some reason, the worksheets in the GChem website are particularly heavy on that, which makes me think that students probably struggle with this a lot. And I feel like I've seen this in organic chemistry as well. Sodium hydroxide is a salt, but it's a strong base. So not all salts are neutral. Sodium chloride is like, literally what we colloquially refer to as salt. So it's neutral because you eat it and it doesn't taste sour, it doesn't taste bitter. It just tastes like salt. Yeah. So I guess in terms of like learning, the neutralization reactions mathematically are really the most straightforward. But students maybe struggle a little bit because there's some chemistry here that you're not familiar with, and maybe that's where some of these issues come in at. So, let's look at another situation here. So let's use this sodium hydroxide example canonically. Yeah, how do we want to do this? Yeah, let's do one more. So let's say you have sodium hydroxide plus HCl. I didn't get any questions about this, so hopefully the reaction itself makes sense. So I take a strong base, a strong acid, I end up getting water and a salt out of it. But let's say that now we're starting with 0.1 moles of this, but we have 0.2 moles of HCl at the beginning. You'll notice I'm using start and finish here. That's just to avoid confusion with equilibrium constants. So you start the reaction, you really are allowing it to come to equilibrium, but I'm just trying to avoid, I know that can be a little bit confusing when you're first starting out. This reaction isn't really, it's not a reaction where you have to worry about the equilibrium, it goes to completion. One question here is, so if another type of salt was formed not in NaCl, would the pH still be 7? And then I had an answer for that, which just depends on the salt. Yeah, that's true. So generally speaking, for a strong acid and a strong base, which is what we have here, strong acid, strong base, whatever the salt is that formed will always be neutral. If it's not a strong acid and a strong base, like let's say this was a weak acid, now your salt is no longer going to be a neutral salt, and you have to worry about how it's going to mess with the pH. That's a harder problem, and we're gonna get to that today. That's good questions. Okay, so at the finish of this reaction, so again, these things react 1 to 1. We're not going to have any sodium hydroxide left over, but we're going to have 0.1 moles of HCl left over, and we're going to form. It's silly to think of water as being 0. It's not really 0, but we're going to form 0.1 moles of H2O, and we're going to form, and again, 0.1 moles of sodium chloride. Okay, so, but now our question is, again, we're just saying, what is the pH of this? What is our pH? So before, all we had to worry about was the fact that we had some sodium chloride and some water. So this side of the equation for the strong acid, strong base doesn't affect the pH at all. That's one way to look at it. So if this is a strong acid, this is a strong base, the products don't actually affect the pH. All that we really care about is what's left over in the reactants. So at the finish, we don't have any hydroxide, but we do have some HCl. And so now we just have to account for that. So it's like saying, what's the pH of a 0.1 molar? So it's like saying, what is the pH of a 0.1 molar solution of sodium chloride and 0.1 molar HCl? With sodium chloride, we don't care about it, doesn't affect the pH, but the HCl does. So now it turns into a strong acid problem where it's just saying, okay, well, HCl is equal to 0.1 molar. So we're still in a liter of water. And so for a strong acid, that's just equal to the H plus concentration. And so our pH is equal to the negative log of 0.1, which is just equal to 1. So the workflow kind of for the neutralization reactions are, and these are going to become important, especially when we get to titrations, is there's this extra step of having to figure out what happens in the neutralization reaction, but then it turns into an ordinary problem that we've sort of already worked on, which is like, what's the pH of, a particular solution, a solution of a particular acid or base. So it's a neutralization reaction. It's sort of a, I guess what I'm saying is if you know how to work the problems where it says, what is the pH of a particular acid or base, regardless of whether it's strong or weak, then neutralization reactions is you're just building on an extra piece right before you do that. So it's the same problem workflow, but now there's a little bit of an extra step beforehand. There's an equation used in homework like OH minus equals square root KBCB. Explain what that is. Homework 4. Let's look at that in office hours. Don't know. Yeah, I don't know what that is. So that's what Gerardo's got it right. Yeah. So sometimes sometimes you'll see people do these oversimplifications of things. Like you'll see this crazy equation written out. Let me see what the square root of KBCB. That comes out of, as somebody pointed out, and this is better for office hours. I'm kind of getting sidetracked here. These equations that you see a lot of times, these are, as somebody pointed out, Gerardo, that these are simplifications from the Rice table, and those are not particularly useful. It's better to just do the Rice table because you can run into problems if you have like acids with more than one protons, or if anything gets like slightly complicated, that equation is no longer valid. And the algebra for deriving the equation is not super hard, and it's much more informative to be able to do it. So try to steer clear of that if they do that, and if they do it in the homework. I don't like those equations. I mean, ultimately you do whatever works for you, but that's my advice, is be able to write out the Rice tables and do that. And be able to derive those equations yourself. Just because we work with equilibrium constants so much in this course. Okay, so yeah, so that's how you get the pH. Okay, so then you can run into these other types of problems though, where you have like, where you're dealing with weak acids or bases. So for weak acids or bases, things get a little messier. Let me get a Ka for a weak acid here. Okay, so let's say that we have sodium hydroxide, but we're going to mix it with, let's use hydrofluoric acid because it's a simple acid. Okay, so same kind of thing. This proton here is going to mix with the hydroxide from the base, and we're going to get water. And then we're also going to end up with the salt, sodium fluoride. So somebody was asking about this earlier, what happens when you don't form a neutral salt? This is an example of that. So this is strong, but this is weak. So that means that our salt over here is going to be, so I guess I should write this out. This is a weak acid. This is a strong base. That means our salt over here is going to be a weak base. Why is that? It's because this is the conjugate base of a weak acid, and the conjugate base of a weak acid is going to be itself a weak base. So weak acids have weak base conjugates, whereas the strong base has its sort of its acidic piece is the sodium plus, and that's not acidic at all. Yeah, I guess I should say like the conjugate base is a weak base, but it's not extremely weak to the point where it doesn't matter, as we saw with like chloride or something. So now we have this. So let's say we do the same problem where we say we start out with 0.1 moles of sodium hydroxide mixed with 0.1 moles of HF. And again, we're just going to stay in 1 liter of water. And we'll say, what is the pH? Okay, so let's take a look then. So at the way to think about this, so this is, I always found this confusing when I was learning this, but like, so, you know, the reality is things don't happen linearly the way I'm about to describe, but it's fine to where it's an easy way to think about it for working problems. So, so if we take 0.1, so let's set up our reaction again. The first step is dealing with the neutralization reaction, and then it becomes a weak acid, weak base problem. Just the standard one that you've hopefully worked on over the weekend. So if I start out with 0.1 moles of this and 0.1 moles of this, just gonna leave the water out. We'll say we start with 0 of this. At the finish of the reaction, we would end up with 0.1 sodium fluoride. So this is the neutralization piece. So you write out the neutralization reaction as if it goes to completion. Okay, so that's like the first step in your mind is like, okay, I get this neutralization reaction, it happens. But now I look at this and I go, oh, okay, but I know that one of these is a weak acid, so that means that whatever I form here must itself be basic. And so now I have the second part of the problem to work at it. So now the problem is, so this is like step 1 here. But now the problem becomes, what is the pH of a 0.1 molar solution of sodium fluoride? So with the sodium chloride situation, it was simple because sodium chloride it's just totally neutral. It doesn't matter. The water doesn't matter one way or the other. If you like, we can put it in. It doesn't affect the overall outcome. So the fact that you form water doesn't matter. You can leave it in, you don't have to, yeah. It doesn't enter into the equilibrium expression one way or the other. Okay. But so now we've got this solution. Now the problem becomes just a weak base problem. And there's a lot of different like kind of riffs on this because it's a strong base. Yeah, if it's a strong base, it dissociates completely. That's true. So step 2 is now figuring out the pH of a weak base. So the problem becomes looking at this equilibrium. And so we would say, okay, we start out with 0.1 molar of this, and we start out with none of either of these. So now it's literally just like a standard equilibrium problem. So write in our rice table. I put in some variables in here to solve. So at equilibrium, I'm going to say that I have the amount of sodium fluoride I have is the amount that I started with after the neutralization reaction minus some amount x, and then I have x equal to these. What I need here, let's see, so let's say that you're given, so let's say for this, they give you the Ka of the reaction, which is 7.2 times 10 to the minus fourth. So something to be careful with here that's confusing a lot of times is that when you write this out, because you're looking at the pH of solution of sodium fluoride, hopefully you recognize, or you get to the point where you can recognize that this is a base. And so what you write out, what makes the most sense to write out, is the reaction of this as a base to form an acid. But the reason I bring that up is because what you're writing out really is the expression for Kb. And a lot of times you're just given Ka, which is sort of the preference in terms of tabulation is we work with Kas or we work with pKas. So just be careful here that you are working with the appropriate equilibrium constant. So if you're given Ka, you have to remember that Ka times Kb is equal to Kw, and that we can very quickly calculate Kb by just taking Kw and divided by Ka. So Kw is always known, that's 1 times 10 to the minus 14th. So I'm just going to take that, I'm going to divide it by our Ka. And so I get Kb is equal to 1.4 times 10 to the minus 11th. And then I can come in and solve this problem. And so I would go through, I'm not going to go through the whole solution because I want to talk more about neutralization, and these take a while to solve. So this becomes like last lecture, like a weak acid, weak base problem. You could probably get away with thinking of x as being very small, and then you just solve this for x. I guess I will actually go through this and solve it because I do want to make some points here. So we're going to say that's approximately equal to that. And so x becomes the square root of 1.4 times 10 to the minus 11th times 0.1. And we want to take the square root of that. Not sure I put that in my calculator right. Let me check real quick. Yep, I was wrong. All right, hold on, I got a question there. So let's see, the question is, can you explain again why we need KB? So KB and Ka have very specific definitions. In this reaction, we're forming a basic salt. This is basic. So if it's basic, the reaction that makes sense to write out is the reaction of a base, which is what we write out here, which is that if I take this base and I add it to water, I'm going to generate some sodium hydroxide. That's just the natural thing to think about when you're adding a base to solution. So I've got fluoride, it's going to react with water, I'm going to generate hydroxide. This reaction that I've written here, though, is an expression of Kb, or results, I guess when you write out the equilibrium expression for it, what you get is the expression for Kb is the right way to say that. So, when I write out an equilibrium expression here, I get Kb is equal to HF times OH minus over sodium fluoride. If I'm given the Ka, that's for a different thing, right? That's for the reverse, not the reverse of this reaction, that's a mistake. It's for the formation of hydronium from hydrofluoric acid. So when you're working with basic salts, the simpler way to say it is when you're working with basic salts, you use Kb. When you're working with acidic salts, you work with Ka. And the reason is that the equation you write out is specific to each of those. We'll work through another, let's see what time it is. We'll work through another problem. All right, so I end up with x equals 1.8 times 10 to the minus 6. So it's important to remember what the hell we're doing when we get to this point. What is x? So x is equal to the sodium hydroxide concentration. It's also equal to the hydrofluoric acid concentration that we form. If we wanted to calculate the sodium fluoride concentration that we end up with at equilibrium, that's equal to 0.1 minus x. But this allows us to calculate the pH now. So if the sodium hydroxide concentration is 1.18 times 10 to the minus 6, we can quickly calculate the pOH. By taking the negative log of that. Right. 5.7. Yeah, that's right. Okay. So I'm not used to thinking in pH. So the pH, so remember that pH plus pOH must equal 14. And so I can quickly calculate now my pH, which is going to be equal to 14, minus the pOH, which is 14 minus 5.7. So I get a pH of 8.3. Okay, so I'll answer your questions in a second. So the pH here is 8.3. I can quickly check to make sure that it makes sense for me. Like, I know I had a basic salt that formed. Let's actually go back and look at this real quick. Yeah, I know I formed a basic salt. So I expect my solution to be slightly basic. And indeed, it is slightly basic. pH 8.3 is just above a neutral pH. Okay, let's see. We got some lots of questions here. Yeah, so this is this problem type, if you want to categorize it, is strong acid, weak base, or weak acid, strong base. One of your components in the neutralization reaction is weak and one is strong. I don't think we'll give you one where they're both weak. That gets kind of miserable. Okay, how do we get to HF and sodium hydroxide as a product reaction? That is the definition of neutralization reaction. You form water in a salt. First reaction of like, so let's just say, okay, lots of questions here. Let's just say the problem results in a strong base would we just plug the molar concentration of the log formula to get POH? Yeah, exactly. If you have strong base left over for reaction, you just use POH. What do we use for POH in the log formula? Sorry, so this concentration, so this is something you want to get fluid with. So you'll notice here I'm writing this as sodium hydroxide. And then over here I'm using, so what I'm saying is sodium hydroxide concentration is equal to the hydroxide concentration, which is equal to X. So this went in here. We don't use the concentration of sodium fluoride to calculate POH because by definition, the POH is the negative log of the hydroxide concentration. So that's a good question, Sonia or Sonia. Okay. So one thing to note here, I think there's some confusion in terms of language, is when you talk about the pH of something, you talk about the pH of a solution. And the pH of the solution is just the hydronium concentration of the solution. It's sort of ignorant of whatever else is present in there. So you can have a lot of other things in there, sodium fluoride or whatever, but you're not talking about the pH of sodium fluoride. You're talking about the pH of a solution of sodium fluoride. So Ka is what we use to describe the strength of an acid. So if you want to talk about, something to do with a specific acid, you talk about its Ka. You could talk about the Ka of sodium fluoride, or the Kb of sodium fluoride, or the Ka of hydrochloric acid, or the Ka of hydrofluoric acid. When we talk about pH, you're strictly talking about a solution. So they're different. They're measures of different things. The pH measures the free hydronium in a solution. The Ka is related to the specific acid. So just be careful with that. I know there's a lot to think about here. It gets confusing. The starting concentrations in this example were just equal molar amounts. Both were 0.1 molar. Okay, so I know there's a lot of questions here. This part, this part here with the neutralization reaction is new. This part down here is from last week. I know putting it all together is complicated, but if you've got the stuff from last week, you've got most of this stuff down already. Let's look at some more neutralization reactions, and I'll talk. If you're struggling with the algebra for let's see, if you're struggling with the second part of the problem, let's say down here, why are we using Kb? What is X? How do I get the POH? That kind of stuff. Save that for office hours. If you're struggling with the neutralization reaction, which is the first part, those questions we can try and get to now. Yeah, so sodium hydroxide and hydrochloric acid dissociate completely. HF does not. That's sort of the key here. Okay, let's look at another problem here. So let's look at the workflow for the problems, and I won't go through the solution part for the second part for solving the pH, just so we can get the neutralization stuff down. So let's look at a variety of scenarios here. Let's say that we start with, so let's assume that we're always in 1 liter of water here, but let's say we start with 0.1 of this, but instead of having 0.1 of hydrofluoric acid, we have 0.2. So again, as somebody asked, I think before, we assume that this goes to completion in the first step. So you think of this as being a stoichiometric reaction, just in a traditional sense of reactions. What's the finish? So at the end of this reaction, what do we have? Starting out with 0, 0. Let's look at another one. Let's work through this one. Let's talk about this real quick. Okay, so we start with 0.1 and 0.2. At the end, since these react 1 to 1, we end up with 0 of this and 0.1 of that. And 0.1 of this. And of course, we form some water as well, but we're not super worried about it. This is, again, we could ask this question more complicated way. At most, it's going to be as complicated as any limiting reagent problem you ever worked in your life. We could give it to you in grams or something if we want it to be particularly cruel. But that's all it really is. This is just a standard limiting reagent problem. It's saying, given a specific reaction, which is this neutralization reaction, given a specific reaction, which is this neutralization reaction, and given not, you don't even have to think about a starting conjugate, but just certain amounts of each one, how much do you have at the end? How much do you form? How much do I have left over? This is just standard limiting reagent type problem. So if you're rough on those, I know those can be a little bit troublesome. Go back and practice some of those, but that's all you're doing. So the first part for neutralization is just a standard stoichiometry problem. But then after that, it becomes a acid-base problem. So now the problem is like this one is actually hard. We haven't really worked at this, but now the problem would be, the first part of the problem is standard limiting reagent. And then the problem becomes, you can write out a new problem for yourself, which what is the pH of a 0.1 molar solution of sodium fluoride and 0.1 molar HF, right? That would be the new problem that we have to work on. That one's kind of tough. You're welcome to go and try that one out. You can work through it with a rice table. There's an easier way to get at it though. We can look at other things here though. Let's look at another one. Let's say you start out with 0.2 of this and 0.1 of that. So again, this is just a limiting reagent problem. I can see that these are 1 to 1. For every mole of sodium hydroxide I have, I require 1 mole of HF. So if I have an excess of sodium hydroxide here, like the ratio is 2 to 1, I know that to finish the reaction, I'm going to have 0.1 moles of sodium hydroxide. All of this will have reacted, and then I will have formed 0.1 moles of sodium fluoride and some water. So now the problem becomes, what is the pH of a 0.1 molar sodium hydroxide solution that also has 0.1 molar sodium fluoride? So this is really the 3 scenarios that you can kind of have. Just assume, so in the neutralization step, work it like it's gone to completion, right? Just work that like you've never even heard of equilibrium. When you're trying to figure out the finish of the reaction, work it like you've never even heard of equilibrium, and you're just trying to figure out what the final products would be in a normal limiting reagent thing. So if you were given this problem in 301, where it says you have 0.2 moles of sodium hydroxide and 0.1 moles of hydrofluoric acid, what are the concentrations? How much sodium fluoride do you form? How much hydrogen fluoric acid do you have left over? And how much sodium hydroxide do you have left over? That is the problem that you're working for a neutralization reaction. It's a standard, I keep saying standard like it's easy. I'm not trying to imply that you should, I mean, you should know it, but I'm trying to imply that this is something you're familiar with, even if you've forgotten it. So we work this out like a normal thing, like I've never even heard of equilibrium. And then I move on to dealing with this equilibrium part of the problem, which is the new part. And so I'm saying, what is the pH of a 0.1 molar solution of sodium hydroxide and 0.1 molar sodium fluoride? And so in one situation, you have equimolar amounts for the neutralization reaction. That's the first one that we worked, where you have 0.1 of this one and 0.1 of the hydrofluoric acid. So 0.1 of this and 0.1 of this. In one, you have excess of the acid, right? That's the situation we're looking at here. In one, you have excess of the strong base. That's the situation that we're looking at here. And each of them leads to their own sort of unique secondary problem, which is, in this case, it's what is the pH of a 0.1 molar solution of sodium fluoride and HF. And this one is what is the pH of a 0.1 molar solution of sodium hydroxide and 0.1 molar sodium fluoride. So neutralization reactions, though, if you're not understanding them, that's okay. I know they're confusing, but I'm trying to be encouraging. I hope it comes off that way. If it feels overwhelming, just try to pause and take a step back from everything that you've recently learned so that you're not getting confused, and work the neutralization part of the problem just as a normal stoichiometry problem. Then write out a second problem for the equilibrium, right? So whatever our finish concentrations are, I'm using the term start and finish, that is what turns into this new problem where you're just saying, well, what is the pH solution that has all of this stuff in it? So work this first part like you've worked problems in chemistry for your entire career. And then the second part is this new equilibrium problem thing. And those are a little bit more tricky. But ultimately, you just end up writing a Rice table out using Ka and Kb. The strong acid and weak base would form water and a weak acid base. So like a weak base would be like ammonia. Yeah. Yes, that is correct, Jordan. Okay. So that's more or less the end of class. I'll take a break and get to office hours. So strong acid and weak base, we need Ka. Strong base, we have, and I hate to give it that in that way. Let's see, strong acid and weak base, you would form a weak acid. Yeah, so you need Ka. And strong base, weak acid, you would use Kb. Yep, that's correct. On Wednesday, where are my notes? Let's see, on Wednesday, we'll probably pick up and work with neutralization reactions a little bit more. And then we'll probably work into buffers. Let's see, is our exam next week or the week after? Week after, good. I was like, man, I feel like we just had one. Yeah, we'll probably get to buffers. I'll have to look at my notes, but yeah, I think we'll talk more about neutralization reactions. We'll talk about buffers, which are it's a more of what we've already learned, but it's just sort of a unique situation where the math gets a little easier. And then I'll try to get us to titrations by Friday, which are usually a little bit painful for people. And then I think that'll get us, and we also have solubility equilibria at some point, but titrations are really where people struggle, but we'll try and work on like next week, just kind of tightening that up. Obviously, there's a lot of stuff to kind of keep track of here. So just keep trying to plug along with problems and trying to build your understanding of your acid-base chemistry. And hopefully everything will just start to come together at some point. I know in the beginning, it's like really amorphous as far as how to solve these problems. So if you're kind of in that state, that's normal, but you don't want to finish out this week still being kind of in that state. You want to end this week at least having moved forward a little bit. If you can get neutralization reactions and kind of just set them up for this next part with the equilibrium, you're in good shape, I think. You at least want to be there by the end of the week. All right, I'll see you guys in a few minutes in office hours. And I'll post some problems solving videos today. I don't think I have any neutralization ones that I've worked yet, but I have some for weak acid, weak base and stuff. So, all right, see you guys in a bit.
Um,
Okay. Let's see. The equation with hydrofluoric acid, why did you write the equation in reverse? The rice table, why sodium hydroxide stuff? People can go over some of the chemical problems. Okay. Yeah, we can do all of those things, assuming we have time. Let's see. So going back here. I wouldn't say I necessarily wrote the equation going backwards. The important thing here, so at the end of the neutralization reaction, my iPad's freaking out. Give me 1 second here. Let me see if I can get this screen to my pencil. Oh, I see. Yeah, there we go. Okay. I see what the problem is. All right. So the important thing to remember here is like so you write out your neutralization reaction. Now you're just looking at what's left over at the end. So, if you follow my strategy here of like, you've got the neutralization reaction happening first, I work it like a normal stoichiometry problem. When I create my new problem, what is the pH of a 0.1 molar solution of sodium fluoride? Then it makes sense to write this problem out in the direction that I wrote it out, because you're not really starting with hydrofluoric acid, you're starting with sodium fluoride. And so you're writing it as the reaction of sodium fluoride, which is a base, to form hydrofluoric acid. Right? If it said what is the pH of a 0.1 molar solution of hydrofluoric acid, then you would write it out in this reaction. It just depends on what your starting species is. So if I'm starting with a base, I'm naturally going to form a little bit of acid. If I'm starting with an acid, I'm going to form a little bit of base. So it just depends on how the problem's written. So if you go back down here, this one, for example, in this problem, you know, here maybe it, well, here you have both present in equal amounts, so maybe it makes sense. Doesn't matter which way you write it. But here, you know, you could write maybe the Ford reaction for HF or something. Yeah, so it just depends on what you're starting with after the neutralization reaction. Why the sodium hydroxide in the second step is 0.2 molar at start and end is 0.1 molar. Yeah, so here it's just, so if we just look at the chemical reaction here, we can think about this. This reaction is a recipe for making, you know, whatever is over here, and it tells me that I need 1 mole of sodium hydroxide for every 1 mole of hydrofluoric acid that I react with. So if I start with 1 mole of sodium hydroxide, I need 1 mole of hydrofluoric acid. If I started with 2 moles of sodium hydroxide, I would need 2 moles of hydrofluoric acid. If I started with 2 moles of sodium hydroxide, but I only had 1 mole of hydrofluoric acid, I would expect to have 1 left over. That's essentially all we're saying here. It's like, it's just a limiting reagent problem. It's like saying, I guess if you're struggling with that, the way to look at it is the neutralization reaction. Would be to say, like, what are the final, wait, I just switched to script. Sorry, my preference is script. But what are the final concentrations of all species for the reaction of 0.2 moles of sodium hydroxide and 0.1 moles of HF in 1 liter of water. Okay, so now we would go through and you would say, okay, well, like, you know, you assume one thing is a limiting reagent, you assume the other thing is, or you start out by just saying, I guess you start out by posing a question. If I have, pick one, if I have 0.2 moles, actually, let me make it easy on myself, I'll pick the right one. If I have 0.1 moles of sodium HF, how much sodium hydroxide do I need to react completely? You'd say, okay, well, 0.1 moles of HF. I look at my reaction stoichiometry up here, which tells me that for every 1 mole of HF that I have, I need 1 mole of sodium hydroxide. And so I see that I need 0.1 moles of sodium hydroxide. So at the end of the reaction, so if the HF reacts completely, that means I've consumed 0.1 moles of sodium hydroxide. So at the end of the reaction, I end up just saying, okay, well, I have 0.2 moles, which is what we started with. And so at the end of the reaction, we have 0.1 mole left over. Right. So this is this is if we were to phrase it like a limiting reagent problem, which is essentially what it is. This might be how you'd work that out in detail. Since we're a little bit further along in our studies in 302, I just kind of do that in my head because this is it's a little bit more. The way I've written up the problems is for them to be straightforward to be done in my head, but this is essentially how you do it. The way we might ask this in 301 would be like, we give this to you in grams to make it a little bit more difficult, et cetera. But that's essentially what this problem is asking. So I keep saying like, this is standard limiting reagent stuff, but I know from working with students that this can be challenging for some students. Like not everybody kind of got that in 301. So if you're struggling with that, just make sure you go back and work some problems. Okay. 20 from the homework, please. Yeah, I can work through one of the problems right above. You're talking about this problem? Josiah, is that how you say your name? Yeah, so for that one, yeah, I'll get to that if I, probably have time. It's only 10:10. I'll get to that one if I have time. For that one, you just end up taking the pH of that solution is dominated by sodium hydroxide. So you can just take the pOH of this and calculate the pH from it. And this ends up being kind of insignificant. But we can work through that. Let me go in order here. Let me see what 25 is on the homework. Are you looking at the extra practice homework problems, Annalie? Oh, the homework that was due last night. Let's see. October 4th. Yeah, this is just a weak acid problem. It's a little bit, well, I don't know. Let's see. So this problem, it says we've got a 0.28 molar solution of weak acid. And it's 3.5% ionized. What is the pH? Okay. I don't know if anilines, yeah, you're supposed to look it up. Either anilines on our, either it's on the GChem website or you just Google it and you see it's an amine or, has a nitrogen in it. Yeah, if something's protonated, it's always a base or something that is, I'm not sure if that's the exact phrasing, but yeah, I think the answer is yes to your question. So for this solution, for this here, all we're doing is you've got some generic acid HA, and it's forming this, and they're telling you it's 3.5% ionized. So they're sort of telling you what the equilibrium concentration is for this. So initially, I don't know if you really want to write out a Rice table for this, but initially you have 0.28 of this, none of this. Let's say none of this. We don't have to worry about the change here. Well, we could learn about the change. The change here will be, so you know it's 3.5% ionized, so you're going to subtract out 0.28 times 3.5 over 100, so 0.035. No, is that the amount? Yeah, and then over here, you're just going to gain that. You gain it for both of them. You don't have to worry about it for both of them, though. And so our final concentration of H plus is equal to this. And so the pH is equal to the negative log of 0.28 times 0.035. Which is equal to somewhere around 2. Yeah, so that's how you work this one out. So this is why it's, like the equations like somebody was talking about in the last class where it's like giving you like H, I think it was like H plus is equal to square root of Ka times HA, those types of things. These are kind of dangerous to just know because like, how would you apply this equation to this situation? You kind of have to like, yeah, you have to develop an intuition around what's going on chemically, and I think that's sort of the intent here, although it's hard. So, but the trick here is just like if it says percent ionized, that's telling you the equilibrium concentration. It's just giving it to you in a different way of saying it. Really, Ka, Kb, all that kind of stuff is a way of expressing percent ionization. But yeah, this is how you work it.
I have a question relating to on the homework problem. It goes over like talking about H2SO4, right? And said the conjugate acid-base pair was HSO4 with only one H. Why do both H's not dissociate? Where you get H2 plus SO4.
Yeah. That's a good question. Let me see what. Let me see a problem. 26, Ian, are you looking at the?
There's like kind of multiple questions related to it.
Okay, is that on the extra practice or is that on the actual homework?
It's on the homework.
That's the aniline question, I see. Okay.
Oh right, no, it's a different one. It's 7 and 8.
7 and 8. Oh, I see. Those are. Um, 7 is kind of tough to go over just because it's like a multiple. It's like pick one. This is a protonic acid base, conjugate acid base, which is not a conjugate acid base pair, respectively. Okay.
Are basically all the acids we're expected to know monoprotic, basically? Or like, are there any like non-monoprotic?
I mean, H2SO4 is one that you should know that's not monoprotic.
Okay.
So first for 7, conjugate acid base pair is always like, it's always comes, at least in the way they're asking it here, it's always HA and then A minus. So you should always have whatever has the proton on the, in this specific question for problem 7 on the left side. And then whatever's deep, whatever's, the conjugate base is, it's just going to be the acid minus the proton.
Oh, okay. Because it says it's
a
base acid, not acid base.
Yeah, it's sort of a really specific way that they're asking it there, because they say respectively conjugate acid base pair. Mm-hmm. For problem 8, is that related to this H2SO4 question that you asked for just now?
Yeah.
So conjugate acid always is just like take whatever the starting thing is and remove 1 proton. So the conjugate base. The conjugate base of H2SO4 is just HSO4. So this is your acid. Mm-hmm. This is your conjugate base. You have to. This is where things start to get confusing. If you want to think of HSO4 as an acid, which it is because it's got another proton, its conjugate base would be SO4 minus 2. So
but acid it's like a weak acid.
It's a weak acid. That's right. Yeah.
Okay.
Yeah. Why is it a weak acid? The answer is more complicated than you want it to be, but generally, each time you remove a proton, it gets harder to remove the next proton after it.
Okay. Yeah.
It's because the simple reason, or one simple reason to look at, is just like building up charge is not favorable thermodynamically. So putting more charge on there just is harder to do. Actually, that's not it. The answer is complicated. Taking off the first proton is easier than taking off the second proton. That's a general trend. So you should expect Ka to always be larger for the first proton.
Okay.
Yep. I can't think of an acid that's strong where it has 2 protons that come off. So like H2SO4, it's like the first proton's a strong acid, the second one's a weak acid. The same is not true for bases though. Like if you look at barium hydroxide, they're both equivalents of hydroxide are strong. So it's a strong base twice.
Yeah.
You get two of this coming off. But for acids, you almost always only have 1 of the protons hopping off.
Okay.
Yep.
Thank you.
Let's see. How does pH change with excess weak acid or excess strong base? Yeah, that's a good question, Maria. And then can you work through a problem right above that? I think those are related. So let's take a look at that. Oops. Okay. So here, so here we've worked through the first part of the problem, which is just working out the neutralization part. And now we're saying, what is the pH of a 0.1 molar solution of sodium hydroxide and 0.1 molar sodium fluoride? So there's a couple of ways to think about this. One is you can think about these two things individually. That's probably the right way to think about it, and think about what their contributions are to the pH. So sodium hydroxide, its contribution to the pH is going to be 0.1 molar. If we want to stick with the format we've been using, you start out with this, 0 of this, 0 of this. At the end, you've got 0 of that, 0.1 molar of that, which we don't care about, but we've also got 0.1 molar sodium hydroxide. So its contribution to the pH, let's put that in orange, comes from the hydroxide. And then we can look at the contribution from sodium fluoride as well. I messed up here. Let's see, so we'd form consistent with how I was doing it before. So what's its contribution? Well, that's a little bit more complicated. So we start out with 0.1 molar of this, and then we have to go through and work through what the equilibrium values are for all of these things. So you're starting out with 0.1 molar sodium hydroxide from up here. And so we're losing X, gaining X, gaining X. And so what you would end up with is some somewhat complicated situation here. We needed a Ka for HF. And so let's see, we could write out an expression for Ka, which is this, that. Shoot, we have to use the Kb, huh? Well, we can write out I'm not going to solve it anyway, but we can write an expression for Kb. I solved this somewhere up the top. Kw. So we've got Kb here, so that would equal this kind of, I don't know how monstrous this thing comes to solve. Sometimes these things work out to be easy, sometimes they work out to be kind of tough. So yeah, so you'd end up with X something something. Well, it might not be that bad to solve. But what you'll find is, let's see, part of me is tempted to just work it out because I'm curious. Let's see, let me go grab Kb from the top here. (1.4 times 10 to the minus 11). What we'll find, though, is that whatever the contribution is from the weak acid doesn't matter. Let me start with that. Yeah, so its contribution to the pH is going to be some teeny tiny amount of whatever this is, right? So this is what we started with for 0.1. That comes from the sodium hydroxide. And then some amount of sodium fluoride is going to generate a little bit of hydroxide in there. How much hydroxide is going to be there? It's going to be very, very small. And so really, what's the pH of this solution end up being? Well, it just ends up being, we can approximate it to be this concentration from sodium hydroxide here. So POH will equal 1, which means that our pH will equal 14 minus 1. So our pH will be 13. How do I know I can do that approximation? So generally speaking, for a solution of strong base and weak base, the weak base contributes little OH minus. So usually it's negligible. So you can imagine that it's not always true that it's negligible. But if you have like a high concentration of sodium hydroxide, let's say, or high concentration of strong base, then the concentration of weak base is going to be insignificant. If you got to a really, 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 really small amount of the strong base, then you might have to worry about the contribution from the base here. If you solve this for X, what you should find is that it's a very, very small number. And I think that equation is pretty solvable, because you don't. I was worried you would end up with a cube term. You don't, though. So yeah. So if you solve that for X, you find that like it's probably like 0.0000000 something. So it's insignificant contribution to the concentration of a hydroxide. So that's how you work that problem. So the same is true if you have a strong. So basically, the lesson is just like if you have multiple species in solution, and one of those is a strong acid or one of those is a strong base, that's going to dominate the pH. That's sort of the lesson there. And to go back to, Ian had this problem earlier, asked about like H2SO4. This is a good example of that. So this thing can dissociate twice. So if you have like a 0.1 molar solution of H2SO4, its pH is just 1. It's the negative log of 0.1. Because the Ka for this is 1.2 times 10 to the minus second. So even though you would form some of this from the H2SO4, the amount of H plus that you end up making in the end from it ends up being insignificant. So it's just another way of saying that it's another way of saying like if you have a strong acid or a strong base in solution, it tends to just dominate everything. So, if you're saying what's the pH of a 0.1 molar solution of H2SO4, okay, this is the strong acid is this, and I'm forming, 0.1 molar of H plus. Yeah, I've got a little bit of weak acid that I also form, but that just doesn't contribute enough for me to even worry about. It just makes my life difficult mathematically to solve it. And it's literally like negligible when most of the time at least, like you'll work it out and, the concentration will be like 0.00000001, which to like even someone who's like obsessive about significant digits, it'll never actually factor in and be meaningful in the answer.
So for the NaF equation, it makes a strong acid and a weak strong base and a weak acid, which is HF, and that HF doesn't contribute much, or is
here
NaF is which one's the weak base or the weak acid?
This is so here we're saying what is the pH of a 0.1 molar solution of sodium hydroxide and 0.1 molar of sodium fluoride? This is a weak base.
Okay.
This is a strong base. Taking the pH for a strong base is straightforward. It's just the negative log. You just work with this. You'd say like negative log of OH minus, and then you could use that to calculate the POH, which you could use to calculate the pH. Taking the pH of this solution, though, like calculating all the species in that, is kind of a pain in the ass. That's when we have to start going to the Rice table. But you can just save yourself that trouble by recognizing that you have a strong base and a weak base, and so you don't have to worry about them, especially if the concentration of this is high, or at least close to being high relative to the other one, to the weak base.
Okay, and it's a weak base because the F accepts a proton.
It's a weak base as far like it's a weak base because it's not on your strong base list.
Okay.
Yeah, I know that's not a super satisfying answer, but yeah, that's why. And it's a weak base because if you're asking just like why we consider it a base, it's because this is a proton acceptor, and it takes a while to kind of. So here's our base, and then like our acid is this, and so that combines with this to make HF.
Okay.
So if you wanted to draw like a mechanism for it, this comes out and grabs that proton. That's the proton accepting. The fluoride is accepting the proton.
Yeah, I had a question about like the Ka, the like 7.2. Are you like getting those values from somewhere? Or are you making them up, like the Kas?
No, yeah, I have a textbook or like a list of KAs next to me that I'm looking at. Yeah, I'm not making
So
this up.
those are corresponding to like the specific ions that you're using.
That's right. Yeah.
Okay.
The Ka is like a tabulated. It's like a tabulated value for a particular reaction. So if you want to know something about it, yeah, any acid that you can think of has probably been explored in some way, and you can look up the Ka value for it, or at least approximate it. Yeah.
But like on the exam, you would just give us the Ka.
Usually, yeah. Like unless we're asking you very specifically to calculate the Ka, we'll give you the Ka or the Kb, and then you use that. The Ka you could think of as being, so for reactions that go to completion, we don't really care about the Ka. You know, like I don't have a Ka for the sodium hydroxide. Ka is just it's just a value that allows you to like work with those reactions and actually figure out, you know, what the amounts are at equilibrium. That's not a very helpful way to say it. You have to, so in that previous problem that somebody asked about where it was like percent ionization, where it's like 3.5% ionization, the Ka value is essentially telling you that. But it does so in a way that's like more general than that.
So if we have
the Ka allows you to calculate, I don't know how to say it without it just repeating the same damn thing. I'm sorry. All right, what were you saying? Is that Taylor?
Since we had sodium hydroxide, which is a strong base, why do we even need to do the whole rice table? Couldn't we calculate it using NaOH?
Yeah, so in this problem that I just worked out where I kind of went through all this stuff, is that the one you're asking about, Taylor?
Yes.
Yeah. You don't have to write out the rice table there. I was just saying that if you wanted to consider the contributions of both species, that's how you would do it. You would say, well, I've got sodium hydroxide with its contribution to pH, and I've got sodium fluoride with its contribution to pH. And so I could say, okay, well, I start out with this much sodium hydroxide, that's its contribution to the pH, and then I could calculate the contribution of sodium fluoride to the pH. But this part down here is superfluous. You don't have to do this, but this is how you would do it if you did do it. Does that make sense? So I'm saying like this is in my mind, like when I think about the problem, I would say, okay, like this contributes to the pH and this contributes to the pH. And if I wanted to figure out exactly how, I would say, this is the reaction for that, and that's the reaction for that. So like as a chemist, that's how I'm thinking about it. But mathematically, it just ends up working out that the second part doesn't matter and we only have to focus on the first part. That's the only point I was trying to make. You don't have to write them both out. It is very good to write them out. For me, maybe this is not true in an introductory class, but for me, like the starting point for chemistry, this should be true probably. The starting point is always to just kind of write out all of your chemical reactions and then start making assumptions about, you know, what counts and what doesn't. That's kind of where I always start at. Because otherwise, I think the reason I do that is the danger of just going, the danger of sort of having like it's like a heuristic where you're like, okay, I've got a strong base and I've got a weak base. The strong base is the only thing that matters. Is there really a danger to that? I guess it's not super dangerous. I don't know.
So we could have just done negative log of 0.1 right off the bat, since that's concentration of NaOH.
That's right. And that's really the lesson, is keep your life simple and just use the sodium hydroxide concentration. Yeah. I guess I wouldn't say it's dangerous necessarily. The more complicated your equilibrium situation gets, the more important it is to write out your reactions. And there are going to be problems where we kind of have to do that. But this is not one of them.
So what like Kb for that equation? Would it make the x significant enough? Would it be like 1.4 times 10 to the negative like fifth, negative fourth? Like
when does it become significant?
Yeah, that you want to.
It depends. It really depends on both. Yeah, let's see. So if you wanted to simplify down here, like say get rid of that. Yeah, you know that there is probably not going to matter. There is probably not going to matter either. So yeah, you could probably do 0.1 x over 0.1 equals kb and solve for x. There's no like, I don't know like how to, I don't know that there's a general way to kind of look at, there's probably a limit that you could put on it, but there's no general way to say like KB is this size, so I know that X is going to be insignificant. But the larger or the smaller KB is, the more insignificant X is going to be. So you've got times 10 to the minus 11th. So that's a really tiny number. Times 10 to the minus 5th is still a really tiny number. Even times 10 to the minus 2nd is pretty small. Really what you want to do is, if you're going through and you're making the approximation, is you take the output from it. So like if you solve for X here, we can do that real quick. It's easy. We could say, let's say we want to just assume that, let's say we want to assume that this is small and this is small, so we want to get rid of that. So we'd end up with 0.1x over 0.1 is equal to 1.4 times 10 to the minus 11th. So I'm making the approximation. I'm just going to assume, oh yeah, so that makes it very easy. So then we see that x is just equal to 1.4 times 10 to the minus 11th. So I make the approximation, right? I just assume that that's going to work. I don't know if it's going to work. And then I take what I get out of it. I take what I get out of it, which is 1.4 times 10 to the minus 11th. And then I come back and I compare it to these other numbers that I made the approximation for. So here I was saying, I'm running out of room here a little bit, but so my above equation, I was saying 0.1 plus x is approximately 0.1, and 0.1 minus x is approximately 0.1. And so I can see if I go back and I plug this number in here, right? That 0.1 plus 1.4 times 10 to the minus 11th really is equal to 0.1 by any approximation, right? It's 0.000000001 plus 0.1. If you want to get more precise about it, you can say you can take x and put it over the original value and see and multiply it times 100 and see what percentage it is. And if this is less than or equal to 5%, then you can say the approximation holds. So that's kind of the way to do it. So you could say, like we could take 1.4 e minus 11, divide it by 0.1, multiply times 100. Yeah, what is that equal to? Some ridiculous, small percentage, 0.000000000000014%. So it's much less than 5%. So we know that the approximation holds. So really what you want to do is you can't really say it up front, but you can make the approximation, solve for x, and then take x and compare it to your original value and say, well, is x a small percent of what the original value is? And if that percentage is less than 5%, then you're solid. So like if you solve for x and x was equal to 0. Let's say 0.5, then your x value would be 50% of your starting value, and then you know that your approximation fails. Okay. So that's kind of the way to do it, yeah. So you make it, you assume it's going to work, and then you check to make sure it did work. Is it true that x is actually small relative to 0.1? Yeah.
For number 12 on the homework, it talks about how for weak acids, a relatively small fraction of the maximum number of hydronium ions is produced. Are there cases where a large fraction is produced, or is it always going to be like a small fraction, basically?
What was I'm sorry, what was the question again? You were saying HCN produces?
It was question 12 on the homework. It said the answer was HCN produces a relatively small fraction of the maximum number of possible hydronium ions.
Sure. Yeah. Yeah, it's always going to be true. All it means is that at equilibrium, you have you don't have 100% of that. So like if you look at HCl, if I start with 1 molar of this, at equilibrium I have 1 molar H plus. Or however you want to think about it. Whereas here, if I start with 1 molar at the beginning, at the finish, I end up with some percentage of 1 molar. So this is not going to equal 1 molar.
Is it usually that less than 5% number earlier?
No. In this case, it really is just like an equilibrium situation. Oh, like I see what you're saying. Like, where's the cutoff for a weak acid versus a strong acid?
Mm-hmm. Yeah.
So for that, we can get a little bit better. So for these, K is almost always less than 1. Usually it's much less than 1. So remember, if K is equal to 1, that means that at 1 molar at equilibrium, you would end up with 0.05 of this and 0.05 of this. Let me make this. Let's go back to equilibrium down here without acids and bases. So like, let's just say you have a really straightforward equilibrium. A going back and forth between B. At K equals 1, that means that if I start out with 1 molar A, at equilibrium, I'll have 0.05 molar A and 0.05 molar B. So K equal 1 means that you have exactly 50% ionization. So as K gets bigger, as K equals 10, for example, right, now things start to get pretty distorted. I think, let's see, I'd have to work through it. I should be able to do that in my head. But I think at K equals 10, now you'd have like, now your ratio would be like 1 to 100. So you'd have like 1% A and 90% B at equilibrium. So if you started out with, so for an initial is 1 molar, 0.1 molar. At equilibrium, so this is our equilibrium. At equilibrium, here you would have 0.1 times 0.01. Right, so once K gets to like even just a value of 10, you start to see that you start to see that it really does start to approximate a reaction that goes to completion. So for K values, K greater than 1 is strong acid. But for practical purposes, for you guys, I think we just give you a strong acid list, you know?
Okay.
Yeah, and you just look up the strong acids on there. But if you look at the strong acid list, you can look up Ka values for them, and you'll see that the Ka values are always greater than 1. You know, you might run into a borderline thing where it's like, if K was exactly equal to 1, maybe you have an acid there that's like somewhere in between a strong acid and a weak acid definition. But certainly for K10 and up, it's a strong acid.
So I think you mentioned it, but when Ka and Kb are less than 5%, they're insignificant, correct?
Oh, like if you're comparing across, yeah, like if you're looking at Ka for this versus, sorry, let me go back. Let's say you're looking at, and we've got Ka1. And we've got Ka2. Yeah, I'm not sure what the hard and fast rule there is, but like, yeah, if Ka, let's see, if you've got Ka2, I mean, divide that by Ka1, multiply that times 100%. Yeah, if that's less than or equal to 5%, let's say, yeah, then Ka2 is insignificant. Yeah, I that probably holds as well, if that's your question. Like if you have two acids, let's say in solution, and one of them's Ka is significantly smaller than the other, which one dominates and what's the cutoff? Yeah, maybe it's something like 5%. We could work through it and probably figure it out. 5% probably makes sense, because that means it only affects the final pH like a tiny amount. So yeah. yes, I guess the answer. 5%. It's tough with these because it's like it's like on the one hand
depends on like the moles as well.
that's
Like because right. Like if the like on the problem above, if the NaOH, if that's like extremely small in moles perspective, and then the other one is higher, then it'll depend on that.
That's right. Yeah, that's exactly right. Yeah, yeah. It's tough to make really really broad generalizations. So that's why the rules are soft, you know. But I guess I would say in an exam situation, we try to give you at least the vast majority of questions, if not all of them, things that are like straightforward, that are not these weird borderline cases. But you know, just be careful around that. Like you're saying, if you end up in a situation where, like if you have sodium hydroxide, but your sodium hydroxide concentration is 1 times 10 to the minus, 10 molar, and then I have sodium fluoride, that's 1 molar. Well, yeah, now, the sodium hydroxide, there's such a small amount of it that it doesn't matter anymore, and sodium fluoride dominates, right? So it's really concentration dependent. This would be a weird one to have because that would make your pH acidic, like let's say -5. Then you might start to get into an interesting situation where like both of those things come into play. But that's atypical for us in terms of giving you test questions, but it's good to at least recognize that can be a problem, or when it would become a problem.
When an acid and a base form together and make a salt, does that salt like almost instantly dissociate?
Yeah, this is something that really bothered me when I was taking this course the first time, is trying to understand like what's happening, because it is this kind of dynamic situation. So, but yeah, yes, I guess the short answer. So it's like, let's give it. So like in the previous example where we're looking at like, was it HF, sodium hydroxide. We write it out like it's a stepwise process like this, but it's not really. It's things are happening all over. There's trillions of molecules in a flask. This thing's happening like as this forms, this is actually dissociating, etc. But you can think about it as happening in 2 steps. So you think about the neutralization happening as its own thing. Imagine that goes to completion, and then the second step is it comes to equilibrium.
Okay. And
so the reality, sorry, go ahead.
Or no, continue, sorry.
I was going to say the reality is that at every time this forms, in reality, it is immediately coming to equilibrium, or very quickly coming to equilibrium with HF and sodium hydroxide. But practically speaking, for solving the problem, we just think about it as happening in 2 separate steps. It's not that it actually, it's not like the reaction has to wait for this to form entirely and then this gets going. That's not how it happens, but it's a useful way to think about it.
Okay. And then earlier in the lecture, you're talking about how NaOH plus HCl forms like water and NaCl.
Yeah. So in that case, no, go ahead.
Why is you said NaCl is basic? Why is that? And what does an acidic salt look like physically?
So NaCl is neutral.
Oh, okay.
Yeah, because it's formed from strong acid and strong base. Mm-hmm. So here we have weak acid. So it's when it's just strong acid or strong base, and those are the only things reacting, things aren't that bad. when you start getting weak acids and weak bases involved, then you have to start breaking out equilibrium constants and making these approximations and stuff like we're talking about. And that's when things start to get a little tough. So yeah, so here, so the situation where you'd have a acidic salt would be like, let's say you had a strong acid and a weak base, like ammonia. Then you would form, this is your NH3 except a proton, so it becomes NH4 plus ammonium, forms Cl minus plus H plus over here. Wait, I screwed that up. No, that's it. Yeah, it doesn't form anything else. It's just the two come together. Yeah, because that makes, okay, we're good. So here we have, this one's weird because you don't form, in most of the other ones you form water, and this one you don't necessarily have to form water. So you have a strong acid though, a weak base. And so what's the salt that we form going to be? It's going to be a weak acid. Because this portion comes from the weak base. That becomes the weak acid on the other side. And then the other portion, the chloride or whatever, right, that comes from the strong acid. So it's just it's a very, very, very weak base where it's considered just neutral. Yeah, a lot of stuff to think about.
Okay.
But those are the three situations you can arrive in. You know, I guess the other one would be like a weak acid, weak base reaction, but we don't really look at those. Those are too much of a pain. Yeah, so there's a lot of scenarios here to look at. And then when we get to titrations in class, that sort of puts everything together. It's sort of every situation rolled up into a single experiment where you take like you can take like a weak base and you do what's called titrating it with a strong acid. And it takes you through every single pH scenario. So that's sort of where everything culminates. But if you can kind of get things down before then, it makes life a lot easier by the time we get there. Other questions?
Can you go over 10 on the homework? I think it's probably like kind of from the last unit.
Yeah. So 10 on the homework is, let's see, which of the following is true in pure water at any temperature? Okay. So pure water, what's true? Yeah, the correct answer is this. So remember, Kw equals this. And so K, let's see, Kw is really defined as 1 times 10 to the minus 14th at 25 degrees Celsius. If we start changing the temperature, Kw changes, but you'll note that no matter what K is equal to, the ratio of H3O plus to OH minus has to stay the same for a neutral solution. That sort of just falls out of this equation at any temperature. Let's see, what are the answer choices here? Yeah, pH and Kw vary with temperature. That's a hint every single time. Kw decreases with increasing temperature. Increases with increasing temperature, yeah. Yeah, I don't know exactly why that should have to think about it. It probably is an entropy thing. Entropy? Yeah, I don't know. Anyway, there's a lot of different options. The main thing to recognize is that all the things we're talking about for pH, like pH equals 7 for neutral. Mostly just these two things, like KW is equal to 1 times 10 to the minus 14, or that pH plus POH equals 14, or that H plus times OH minus equals 1 times 10 to the minus 14. All of this stuff, these values are like dependent on the temperature. And so that's not always true. But even if this value changes, this relationship still holds. So like this expression is always true. It's just that the value of K is not always constant. That's the main thing. So or I should say that it's always constant at constant temperature. So if you start screwing with the temperature, you're screwing with the value of K. But recognizing that no matter what case, like if K is equal to 1 at neutral, this still has to be true. Maybe these values are very different, but they're still equal to one another. So that's why the answer ends up being that H plus must always equal OH minus. Yeah. I think the main thing to get there is just that pH and KW vary with temperature.
Okay.
Yeah. All right, well, that brings us to conclusion for office hours. Yeah, I mean, if you're working problems, you're coming to office hours, going to the TA office hours, you're doing all the right stuff. It just takes a while to get this stuff. So if you're confused right now, that's where you probably should be. But hopefully by the end of this week, if you keep at it, things start to kind of clarify a little bit. But you guys are asking really good questions, I think, especially about like when things are true and when things are not true, based on the Ka values or for those approximations and stuff. That's the right way to think about these things. So, all right. Yeah, I'll see everybody on Wednesday.
Thank you. Have a good day.
Yeah.